Okay, so this week we're going to finish up, and today we want to have a look at the problem of the qibla. So you're probably asking, what is a qibla? Well, if you go to a mosque, it'll be a very fancy thing on one wall, and it indicates the direction in which Mecca is, so that when people are in the mosque praying, they can pray towards Mecca. And so this determining that then, the direction of prayer was a problem that a lot of the Islamic mathematicians worked on in the medieval times. So we're going to look at what al-Biruni said. So remember Al-Biruni, he was the one who measured how high the mountain was, and then measured and used that to measure how big the earth was. So he wrote a book called The Determination of the Coordinates of Cities, and it's kind of the major medieval text on geography. And in there he writes, through the determination of position is an end in itself, which satisfies an investigator. It is our duty to find an application for such a determination that is beneficial to the populace of the whole region, whose longitude and latitude we have surveyed, or to a particular section of it exclusively. Let the universal benefit be the determination of the azimuth of the qibla. So he's saying there that, this problem is, it's good enough just to do as a problem. We should do math just because we love math. But hey, this actually is really useful because we can determine where to put the qibla. And then very interestingly, he also mentioned Jews and Christians. Like, Jews need to face Jerusalem when they pray, and Christians need to face east when they pray. And he wrote, I have no doubt that it is useful to peoples of all faiths. So I found that kind of very pleasant, this kind of tolerant message that was in there. So al-Biruni is actually famous because when he went and determined the height of the mountain, he was in India, and he wrote a book on India. And so he's actually considered one of the first anthropologists. He was a very interesting guy. Okay, so what is the problem? So why is this a problem with spherical trigonometry? So let's have this situation here. So this is a slice of the world. So there's the North Pole, there's the equator. So here's our two places. So we're at Z, and M is Mecca. And so these lines here are meridians of longitude. And so what we want to figure out is what this angle is here. And so that will give us the direction where Mecca is. So what do we know? We know the latitude and longitude of our places. And so that's actually one of the things in the book, is to figure out how to figure out latitude and longitude. Latitude, as I said before, is a fairly easy task to do. It just involves just measurements of the sun at noon. So from the angle that the sun makes, you can fairly easily figure out latitude. Longitude actually is a much harder problem. As I've said before, longitude is really a problem of time. So if you want to figure out longitude, well, first off, you need a base longitude. And so we use Greenwich, but that has not always been the case. A few years ago, it was interesting, in the University Art Gallery, they had an exhibition of old maps, and there was a map of the US from like the 1870s, and they had the zero longitude going through Washington. And if you go to maps at the same time, the zero longitude, a French map will go, zero will go through Paris, etc. Actually, what it usually, it went through, in America, it went through the National Observatory, which is at Washington. And in other countries as well, there'd be a national observatory, and that's what would determine where the zero longitude was. And so then to super accurately do the longitude, you'd have something like when there was the eclipse. So lunar or solar eclipse is great. You know what the time is that the eclipse happened at one spot. You know when the eclipse happened at the other spot, and you just look at the difference of the time, and 1 hour equals 15 degrees. So yeah, so I think at one point Christopher Columbus, when he was in the West Indies, there was a solar eclipse or something like that, and he was able then to determine the longitude of the Hispaniola. What's that island? Yeah, the island, Haiti and Dominican Republic. What do they call that island? Hispaniola. Anyway. So yeah. So okay. So there's the problem. So we see that we have a spherical triangle here, right? So we've got the meridians of longitude here, and here is the great circle joining where we are with Mecca. Now, because we know the latitude, right? The latitude is going to be this arc here, and it's going to be this arc here. So this is going to be 90 minus the latitude of Z, and this is 90 minus the latitude of Mecca. This angle here is just going to be the difference between the longitudes of the two places. Okay, so there's a problem. We can't use the sine rule. Why is that? Why is the sine rule? So if we know this side and this angle, why can't we use the sine rule? What do we need to be able to use the sine rule? Yeah, you need a side and the opposite angle to be able to use the sine rule. So one triangle that can be easily solved is this triangle here. Okay, and so we don't really. This angle here is just the difference of longitudes. What's this angle here and here? 90 degrees, because it's a meridian cutting through the equator. So already we see that the size of this triangle is 90 plus 90, 180 degrees plus whatever the difference in longitude here. So again, you can see that the angular excess, the excess of 180 degrees tells you how big that triangle is. Because the bigger the difference in longitude, the bigger that triangle is. Okay. What is this side here? Between the pole and the equator, it's just 90 degrees because it's a quadrant. So this is 90 degrees, this is 90 degrees. So remember, angles measure sides as well as angles. What's this length here? It's exactly the same as this angle here because this is a quadrant. So this difference of longitudes is not only this angle here, but it's also the same thing as the length of this side here. Okay, but we have to solve this triangle. Well, in particular, we want to find this angle. So what do? So Al-Biruni gave 4 different solutions, and that should make you groan a little, because if there's 4 different solutions, that means the solutions must be complicated enough to justify having 4 different ones. But the standard thing that you do in these situations is to put yourself at the center. So this is where we are now. So that Z, we can see why we called it Z, because Z stands for zenith. So this is now that, if we think of this as the celestial sphere, Z is now the celestial zenith. M here is the celestial zenith of Mecca. And here is our North Pole. Here's the celestial North Pole here. So this line here is our local meridian. So at our meridian of longitude that goes between the pole and Z. And so here is, so this circle here is the horizon. So this is the north part of the horizon. This is the south point of the horizon. Okay. This line here then is the great circle that joins our point to Mecca. And this line here is a great circle, is the meridian of Mecca. Okay, and so we are wanting to figure out this angle here. Sorry, it got turned over, turned 180 degrees. So I'm from Australia, so I don't mind south being on top, but it might make you uncomfortable. Notice that this angle here is the same thing as this length here, because it's a pole. This is now a quadrant, so lengths become angles. Okay, so when you're doing spherical trigonometry, the big inconvenience is that triangles no longer add up to 180 degrees. So you can't kind of rely on that. But what makes up for it is the fact that you've got poles. And once you've got poles, then, you know, so this length here, this length here, this length here is all 90 because it's a pole. This length here is this angle here. So you can take advantage of poles to get things done. Okay. So let's do some stuff. Okay. So now we draw in the horizon for Mecca. And so F is the place where the horizon for Mecca crosses the meridian. And then we have here, we have the horizon for F. Okay, and as I said before, this is the meridian of longitude. So now we've got enough stuff to figure out this green rectangle. Pn is going to be the same thing as the latitude of our Z here. PL is going to be the same thing as the latitude of Mecca. So MP is going to be 90 minus PL. So that's going to be 68 degrees 15 minutes. So again, because remember M is a pole for this, so this whole length here is 90. ZPM, which is this thing here, right, is just the difference between the two longitudes. And PHM, this thing here, that's 90 degrees, right? Because this is a horizon for F. So the angle that it makes here is 90 degrees. Okay, so we've got data for that triangle, so we can use the sine law for that triangle to figure out what this length is. All right, so the sine law will tell us what the sine of that is in terms of data that we know, and so then we can solve to figure out what that length is. This length here, then, which is going to be the same thing as this length here, which is the same thing as PFL, as same thing as this angle here, right? Because this is F, remember, was a pole for this, is going to be 90, right? Because this is a pole for this horizon there, 90 minus NH. So we can figure out what this length is here. And also, this angle equals the same as this angle. So we've still got the same thing about when you have lines that cross over, the angles opposite each other are going to be the same. Okay. And so now we can solve this red triangle here. We've got enough data for that to use the sine rule for that. And so we can figure out what this length is. And so then we can figure out what this length is, right? Because it's going to be Pn minus Pf. And then so we can figure out what Zf is, because again, this is 90 degrees. If we know what this is, we can figure out what that is. Then we can use the rule of four quantities on this configuration here, right? Because here we have a set of right triangles, one nested within the other. So that's what we can use the rule of four quantities for, to figure out what Zi is, Zi being this quantity here. So we can figure out what IQ is, right? Because again, this is 90 degrees, it's a pole, so IQ is 90 minus this. But G is also a pole with this equator. So this angle here is the same thing as IQ. And so finally, we can apply the sine rule to this blue triangle here, and we can figure out what Gn is. And since Kg is 90 degrees, we can figure out what Kn is, and that's the qibla. So don't worry, I'm not going to ask you to do this. I just want you to see the kinds of tricks that go on when you do a spherical trigonometry problem. So we had to, what we had to do, we had to apply the sine rule 3 times and the rule of four quantities once. So we had to do 4 things to figure things out. And so that's, so did I say that the example that I'm using here was, I was letting Z be Jerusalem and M be Mecca. And so this is the direction for the qibla in Jerusalem. Okay. Is there an easier way to do this problem? Think about if you had a triangle and you knew this angle and you knew these sides. And you wanted to find x. What would be the trig identity you would use to solve for x? Exactly, which is the x squared equals, what is it? B squared plus c squared plus the 2bc cosine a, something like that. Does that look right? Or is it minus? I think it's plus. Right, because when this is 90 degrees, this is 0. Okay, that doesn't help me till with plus or minus. Sorry, I can't see. Anyway, we need a spherical cosine rule. which Al-Biruni didn't know, but later on there was one, and it's something like cosine of A equals cosine of B times cosine of C. Right, because that's the, remember, that's the Pythagorean theorem for spherical triangles, just like, so remember the cos rule can be thought of as a generalization of Pythagoras theorem. And then what you're going to have here, you're going to have something like 2 sine B sine C cosine A. And if this is a plus, if this is a plus, and it's a minus, if that's a minus. So the cos rule goes over to the spherical. And so you can see that if we had a cosine rule, then we could have figured out this length directly. And then once we have this length, then we could use the sine rule to figure out what this angle was. No problem. But I still wanted to show you that because it's very typical spherical trig, that problem there. Okay. I think that's what I want to say today. So tomorrow, Thursday, we'll wind up. I think I'll talk a little bit about instruments and tables, and then kind of do like a wrap up of everything we've done. Okay, any questions about anything? So you've got a homework that's going to be due Friday, and then a final homework which is going to be due sometime in the final week. And then I'll probably need to have office hours after Thanksgiving. I'd be appreciative of any feedback for when you'd want those office hours to be, whether you'd want them in the week before finals or the week of finals or whatever. But we'll sort. So think about that, and we'll discuss that on Thursday as well. Okay.